The frozen realms of our planet tell a story written in Issa narrative spanning millions of years. Etched into glaciers, ice sheets, and ancient sediments. Today, ice in its myriad forms blankets approximately 16% of Earth's surface. During the peak of northern winter, when the northern hemisphere tilts away from the sun and temperatures plummet, this coverage expands to encompass roughly one-third of all land areas. These vast expanses of frozen water are far more than mere scenic backdrops or inconvenient obstacles to navigation. They represent one of the most powerful forces shaping our planet's climate system, influencing everything from global temperature patterns to ocean circulation, from weather systems to the very habitability of coastal regions where billions of people make their homes. Glaciers, those massive rivers of ice that carve through mountain valleys and polar landscapes, act as enormous frozen reservoirs. Permafrost, the permanently frozen ground that underlies vast stretches of the Arctic and subarctic regions, locks away organic matter and gases that have accumulated over millennia. Ice sheets, those continental-scale masses of ice covering Greenland and Antarctica, contain enough frozen water to dramatically reshape our world's coastlines if they were to melt. Snow cover, refreshed annually across large portions of the planet, creates a brilliant white blanket that plays a crucial role in Earth's energy balance. Together, these components of the cryosphere frozen water system function as a planetary thermostat, helping to regulate temperatures and drive the great ocean currents that distribute heat around the globe. The reflective properties of ice and snow, known scientifically as albedo, constitute one of their most important climatic functions. When sunlight strikes these bright surfaces, as much as 90% of that solar energy bounces back into space rather than being absorbed by darker land or ocean surfaces. This reflection effect helps keep our planet cooler than it would otherwise be. The ice sheets and glaciers also shape ocean currents in profound ways. As ice forms in polar regions, it excludes salt from its crystalline structure, making the surrounding seawater more saline and therefore denser. This dense, cold water sinks and flows along the ocean floor toward the equator, while warmer surface waters move poleward to replace it, creating a global conveyor belt of ocean circulation that redistributes heat across the planet. Furthermore, the temperature contrasts between ice-covered regions and warmer areas generate atmospheric pressure differences that spawn weather patterns, influencing precipitation, storm tracks, and seasonal variations far beyond the polar regions themselves. Yet despite their apparent permanence and their crucial role in maintaining climate stability, there are increasingly clear signals that Earth's great stores of ice have begun to undergo significant changes. Satellite observations, field measurements, and long-term monitoring programs have detected accelerating rates of ice loss in many regions. Glaciers and mountain ranges from the Alps to the Andes, from the Himalayas to the Rockies, are retreating. Arctic sea ice has declined dramatically in extent and thickness over recent decades. Ice shelves fringing Antarctica have collapsed in spectacular fashion. The great ice sheets of Greenland and Antarctica, once thought to be relatively stable on human timescales, are losing mass at rates that have surprised many scientists. These changes are not occurring in isolation. They are part of a broader transformation of Earth's climate system driven by rising concentrations of greenhouse gases in the atmosphere, primarily from the burning of fossil fuels and changes in land use. To understand where our planet might be headed, scientists have undertaken an ambitious quest to read the historical record, preserved in ice itself and in the geological traces left by ancient climates. They drill deep into ice sheets, extracting cores that contain tiny bubbles of ancient atmosphere, dust particles from long-ago volcanic eruptions, and chemical signatures that reveal past temperatures. They scour ancient seabeds for fossils and sediments that tell of vanished ice ages and warm periods when sea levels stood higher than today. They analyze the chemistry of cave formations, tree rings, lake sediments, and coral reefs, each natural archive contributing pieces to the puzzle of Earth's climate history. Through this painstaking detective work, researchers are learning not just about what happened in the distant past, but about the fundamental mechanisms that drive climate change, and about the potential consequences of the transformation currently underway. What are they discovering about the fate of our planet not just in the coming decades or centuries, but 1,000 years into the future and even beyond? The answers emerging from this research are both fascinating and sobering. They reveal a planet whose climate has undergone dramatic swings between ice ages and warm periods, driven by a complex interplay of factors ranging from subtle changes in Earth's orbital geometry to catastrophic volcanic eruptions, from the evolution of life itself to the slow dance of continents across the globe's surface. These discoveries provide essential context for understanding our current situation and for anticipating what the future might hold. The descent into ice. To understand the present and future, we must first journey into the past. Approximately 30,000 years ago, Earth entered a relentless descent into winter. This was not a sudden plunge but rather a gradual cooling that would eventually culminate in the last glacial, maximum around 21,000 years ago. Global temperatures dropped significantly below those of today. Glaciers that had been confined to high mountain valleys and polar regions began their inexorable march into areas that had enjoyed temperate climates for thousands of years. In North America, massive ice sheets pushed southward from Canada, eventually covering much of what is now the northern United States. Similar ice advances occurred in northern Europe and Asia. These were not mere expansions of existing ice fields. They were transformations of the landscape on a continental scale. Ice spread beyond the polar seas, extending the reach of frozen ocean far into regions where open water had once dominated. The formation of extensive sea ice had profound effects on ocean circulation and on the exchange of heat and moisture between ocean and atmosphere, as more and more of the planet's water became locked up in ice sheets and glaciers. Sea levels dropped dramatically, eventually falling to about 120 meters below present levels. This exposed vast areas of continental shelf that are now submerged, creating land bridges that allowed plants, animals, and eventually humans to migrate between regions that are today separated by ocean waters. The Bering Land Bridge, connecting Asia and North America, is perhaps the most famous example, but similar connections emerged between Britain and continental Europe, between many Indonesian islands, and between other regions now divided by shallow seas. The ice sheets themselves grew through a process of accumulation that played out over thousands of years. Each winter, snow fell on the high plateaus and in the polar regions. In the coldest areas, this snow persisted through the summer, gradually compacting under its own weight and transforming into dense, crystalline ice. Year after year, century after century, millennium after millennium, new layers accumulated on top of the old. The weight of accumulating ice was so immense that it literally pushed the land surface downward, a process called isostatic depression. The bedrock beneath the ice sheets flexed and flowed like a viscous fluid over geological timescale, sinking down under the burden of ice that could reach 3 or even 4 kilometers in thickness. Nowhere is this process more dramatically illustrated than in Greenland, where new layers of ice accumulated on the vast frozen plateau that covers most of this enormous island. Greenland's ice sheet today stands as a monumental formation, a frozen fortress built over successive ice ages spanning millions of years. At its thickest point, the ice reaches depths of approximately 3 kilometers. That's nearly 2 miles of compressed snow and ice, representing hundreds of thousands of years of accumulation. The sheer mass of this ice has had a profound effect on the island's geology. So heavy is the ice sheet that it has pushed much of Greenland's bedrock down below sea level. If we could somehow instantly remove all the ice, we would find that large portions of the interior form a bowl-shaped depression, with bedrock surfaces lying hundreds of meters below the current sea level. Over thousands of years, the rock would gradually rebound, rising back toward its original position, a process we can observe today in regions that were covered by ice during the last glacial period, but have since been freed from that burden. The ice sheet doesn't just sit there like a static dome. However, despite its apparent solidity, ice is actually a viscous material that flows under pressure. The ice in Greenland's interior gradually deforms and moves under its own weight, flowing outward toward the coasts in a slow but inexorable motion. This flow is channeled by the underlying topography, creating streams of ice that move faster than the surrounding mass. Eventually, this flowing ice reaches the coast, where it either melts, calves off as icebergs, or forms floating ice shelves that extend out over the ocean. The entire system exists in a delicate balance between accumulation in the interior, where snow continues to fall and compact into ice, and loss at the margins through melting and calving. When accumulation exceeds loss, the ice sheet grows. When loss exceeds accumulation, it shrinks. Questions of resilience. Yet today, despite its immense scale and its ancient origins, scientists have begun to ask profound questions about how resilient Greenland's ice sheet really is in the face of changing climate conditions. These questions are driven by measurements, showing that average global temperatures have risen approximately 1 degree Celsius since the Industrial Revolution, the period beginning in the late 18th and early 19th centuries when humans began burning fossil fuels on a large scale, releasing carbon dioxide and other greenhouse gases into the atmosphere. While 1 degree might not sound like much, it represents a significant shift in the global energy balance, and its effects are not distributed evenly. The Arctic has warmed at roughly twice the global average rate, a phenomenon known as Arctic amplification. This enhanced warming occurs because of several feedback mechanisms. As ice and snow melt, they expose darker surfaces that absorb more solar energy rather than reflecting it back to space. As the ocean warms, it releases more water vapor, itself a greenhouse gas. Changes in atmospheric circulation can amplify regional warming trends. Climate models and projections suggest that global temperatures could rise by another degree, or even more by the end of this century. Depending on future greenhouse gas emissions, some scenarios project warming of 2 degrees Celsius or more above pre-industrial levels. For Greenland, already experiencing enhanced Arctic warming, This could translate into temperature increases of 3 to 5 degrees Celsius, or even higher. Such warming would have profound implications for the ice sheet stability. If Greenland's ice sheet were to melt, completely a process that would take centuries or even millennia, but which might become inevitable. Beyond certain temperature thresholds, sea levels around the world would rise by over 7 meters. That's more than 23 feet of sea level rise, enough to fundamentally redraw the world's coastlines. Asterisk, to put this in perspective, a 7-meter sea level rise would destroy or threaten the homes and livelihoods of up to a quarter of the world's population. Hundreds of millions of people live in coastal areas that would be completely inundated. Major cities would face existential threats. Infrastructure worth trillions of dollars would be at risk. Agricultural lands would be lost to saltwater intrusion. Freshwater supplies would be contaminated. The social, economic, and political consequences would be almost unimaginable. And this considers only the ice in Greenland. Antarctica holds far more ice, with the potential to raise sea levels by more than 60 meters if its ice sheets were to melt completely. Though this would require even more extreme and prolonged warming. Asterisk. Elevation maps of coastal regions around the world dramatically illustrate the areas that would be affected by a significant sea level rise. Regions shown in black and red on these maps represent areas less than 10 meters above current sea level, the areas that would be most immediately threatened by the melting of green ice and by the initial impacts of Antarctic ice loss. Consider the southeastern United States, where vast areas of Florida would simply disappear beneath the waves. The Louisiana coast, already subsiding and losing land to erosion, would see New Orleans and other communities overwhelmed. Bangladesh, a nation of more than 160 million people, where much of the country lies barely above sea level, would lose huge swaths of territory, potentially displacing tens of millions. The Persian Gulf region, with its major cities and crucial energy infrastructure, would face severe flooding. Parts of Southeast Asia, including portions of Vietnam, Thailand, and Myanmar, would be inundated. China's coastal regions, home to hundreds of millions of people, and including major economic centers like Shanghai, would face grave threats. Asterisk, and this is just the beginning. These are merely the most immediate and dramatic impacts. Sea level rise of this magnitude would also increase the frequency and severity of coastal flooding during storms, contaminate coastal aquifers with saltwater, destroy crucial ecosystems like mangrove forests and coral reefs that provide natural coastal protection, and trigger massive human migrations as people flee affected areas. The geopolitical implications, including potential conflicts over resources, migration, and territory, add additional layers of concern. The economic costs would be measured in the tens of trillions of dollars. And some losses, cultural heritage sites, unique ecosystems, indigenous homelands would be truly irreplaceable. Asterisk, with so much at stake, the scientific community has mobilized an unprecedented effort to monitor Earth's frozen zones. Satellites equipped with sophisticated sensors orbit overhead, measuring ice extent, thickness, and flow rates. Radar instruments can peer through clouds and operate in the darkness of polar winter, providing year-round coverage. Laser altimeters measure minute changes in ice sheet elevation with precision measured in centimeters. Gravity sensors detect changes in ice mass by observing tiny variations in Earth's gravitational field. Aircraft carry ice-penetrating radar systems that reveal the internal structure of glaciers and the topography of the bedrock beneath ice sheets. On the ground and on the ice itself, teams of researchers establish monitoring stations, drill ice cores, and deploy instruments to measure temperature, ice motion, and meltwater flow. Ocean sensors track changes in seawater temperature and salinity that might affect ice shelves and marine terminating glaciers. Asterisk, scientists are also engaged in extensive efforts to reconstruct past climates, searching for clues about where Earth might be headed, not just in the coming decades or centuries, but thousands of years into the future. This paleoclimate research draws on evidence from a remarkable diverse array of sources. Geological traces of past sea levels, ancient shorelines now stranded high above, current seas or submerged beneath them reveal how much ice existed at different times in Earth's history. The distribution of fossils tells us which plants and animals lived in particular regions, providing insights into past temperature and moisture conditions. Chemical traces preserved in ocean sediments correspond to ancient ocean temperatures and can be measured with sophisticated instruments. Ratios of different oxygen isotopes in ice cores, cave formations, and marine sediments serve as temperature proxies. Pollen grains preserved in lake sediments reveal the vegetation that surrounded those lakes in ages past, and from that we can infer climate conditions. Deep time, Earth's Ice Age history. Asterisk, when we look back across the vast expanses of geological time, extending over more than 2 billion years, we find that Earth has experienced 5 major glacial periods, or ice ages. Each of these represents an extended interval of time, often lasting millions of years, during which the planet was much colder than today, and substantial ice sheets existed even in regions far from the poles. Between and within these ice ages, the climate varied considerably, with warmer periods allowing ice to retreat and colder periods seeing its advance. Understanding these ancient ice ages and the forces that drove them provides crucial context for interpreting current changes and anticipating future ones. Asterisk, the first major ice age, known as the Huronian glaciation, occurred approximately 2.4 to 2.1 billion years ago during the early Proterozoic eon. This ancient ice age has been linked to one of the most significant biological revolutions in Earth's history: the rise of photosynthesis in primitive organisms. Early photosynthetic bacteria evolved the ability to capture sunlight's energy and use it to convert carbon dioxide and water into organic compounds, releasing oxygen as a waste product. As these organisms proliferated, they began to fundamentally alter Earth's atmosphere. They took in vast amounts of carbon dioxide, an important greenhouse gas that traps solar energy in the atmosphere and keeps the planet warm. As atmospheric carbon dioxide concentrations decreased, less solar energy was trapped, and the planet cooled. This cooling effect was likely amplified by other factors, but the biological transformation of the atmosphere appears to have been a crucial trigger. The result was a deep freeze that locked much of the planet in ice for millions of years. Asterisk, the second major ice age, often called the Cryogenian period and sometimes referred to as Snowball Earth, began roughly 720 million years ago and lasted, with interruptions, until about 635 million years ago. This was perhaps the most severe ice age in Earth's history, so extreme that some evidence suggests ice may have extended nearly to the equator, creating a planet almost entirely covered in ice, hence the Snowball Earth moniker. The causes of this extreme glaciation remain debated, but likely involved a combination of factors including the configuration of continents, volcanic activity, changes in atmospheric composition, and feedback mechanisms that amplified the cooling. The existence of such a severe ice age is supported by geological evidence, including glacial deposits found in rock formations that we know, from paleomagnetic studies, were located near the equator at that time. The fact that life survived this frozen period, and indeed that complex multicellular life evolved shortly afterward during the Ediacaran and Cambrian periods, is testament to life's resilience, but also shows how profoundly ice ages can affect Earth's biosphere. Asterisk, the third and fourth major ice ages, known as the Andean-Saharan glaciation and the Karoo glaciation, occurred approximately 460 to 430 million years ago and 360 to 260 million years ago, respectively. These ice ages occurred during periods when life was diversifying and colonizing the land. Plants were spreading across the continents, and their presence began to have significant effects on climate through several mechanisms. Plant roots broke down rock through physical and chemical weathering, a process that consumes carbon dioxide from the atmosphere. Plants also increased the retention of moisture in soils and the return of water to the atmosphere through transpiration, affecting precipitation patterns. The evolution of large woody plants and forests during the Carboniferous period, within the time frame of the Karoo Ice Age, led to massive burial of organic carbon in what would eventually become coal deposits. This removal of carbon from the active carbon cycle likely contributed to cooling by reducing atmospheric carbon dioxide levels. Asterisk, finally, we have the Quaternary glaciation, which began approximately 2.6 million years ago and continues to the present day. Yes, technically, we are still in an ice age, or more precisely, in an interglacial period within an ongoing ice age. The Quaternary has been characterized by repeated cycles of glacial advance and retreat, with major ice sheets growing and then melting away roughly every 100,000 years. These cycles have shaped the landscapes we see today, carving valleys, depositing sediments, and leaving behind the moraines, erratics, and other features that geologists recognize as signatures of past glaciation. Modern humans evolved during this ice age, and our species' entire history has played out against the backdrop of these climatic oscillations, the relatively stable and warm conditions of the current interglacial period. The Holocene epoch of the past 11,700 years or so have provided the climatic foundation for the development of agriculture and civilization. The world takes shape to understand the glacial cycles of the Quaternary Ice Age. We need to examine the planetary conditions that set the stage for their emergence. During the period from roughly 90 to 50 million years ago, during the late Cretaceous and early Cenozoic eras, the world was taking on its modern form. The continents, which had once been joined in the supercontinent Pangaea, were moving toward their present positions through the slow but inexorable process of plate tectonics. The Atlantic Ocean was widening as the Americas separated from Europe, and Africa, moving westward at rates of a few centimeters per year. India, having broken away from Africa and Madagascar, was on a collision course with the southern margin of Asia. The impact of this continental collision would eventually thrust up the Himalayan mountains and the Tibetan Plateau, the highest and most extensive highland region on Earth. During this period, the world was generally much warmer than today. there were no significant ice sheets, even at the poles. Antarctica, not yet positioned over the South Pole and still connected to South America and Australia, supported forests. The Arctic Ocean was much warmer than today. Crocodiles and palm trees existed at high latitudes. This warm climate was sustained by high levels of atmospheric carbon dioxide, probably several times higher than pre-industrial values, which created a strong greenhouse effect. The sources of this CO2 included volcanic activity, which was elevated during this period of active seafloor spreading and continental movement, and possibly the release of carbon from methane hydrates in ocean sediments during periods of ocean warming. Global temperatures spiked dramatically, roughly 55 million years ago, during an event known as the Paleocene-Eocene Thermal Maximum, or PETM. This extraordinary episode of warming saw temperatures rise by about 5 to 8 degrees Celsius. In just a few thousand years, a rate of change that, while slower than current warming in terms of absolute speed, was extremely rapid by geological standards. Arctic temperatures may have exceeded 23 degrees Celsius, similar to modern subtropical regions. Ocean temperatures at depth also increased significantly. The cause appears to have been a massive release of carbon into the atmosphere and oceans, possibly from the destabilization of methane hydrates on the ocean floor, from volcanic activity, or from a combination of sources. The amount of carbon released has been estimated at several thousand gigatons, comparable to the total amount of carbon in all of Earth's proven fossil fuel reserves. The PETM provides a natural experiment that helps us understand the effects of rapid carbon release and warming. Evidence from this period shows major changes in ocean chemistry, including acidification caused by the absorption of excess CO2. Marine organisms that built shells from calcium carbonate suffered significantly. On land, the warming caused major shifts in vegetation zones and animal distributions. Many species went extinct, while others migrated to higher latitudes. There were also significant changes in precipitation patterns, with some regions experiencing enhanced monsoons and others becoming more arid. The climate system took roughly 150,000 years to recover from this perturbation, as natural processes gradually removed the excess carbon from the atmosphere and oceans. This long recovery time is sobering when we consider that human activities are currently releasing carbon at rates potentially as fast as, or faster than during the PETM. However, following the PETM, the stage was being set for a major cool that would eventually lead to the Ice Age conditions of the Quaternary. Several factors contributed to this long-term cooling trend, which took place over tens of millions of years. One crucial factor was the changing configuration of land masses and ocean basins. As the continents continued their slow drift, the Arctic Ocean became increasingly isolated from the wider oceans. By about 50 million years ago, the northern polar region was largely enclosed by land masses North America, Greenland, Europe, and Asia, with only narrow passages connecting the Arctic Ocean to the Atlantic and Pacific. This configuration restricted the flow of warm water from lower latitudes into the Arctic, allowing cold conditions to develop and persist in the far north. The isolation of the Arctic allowed a layer of fresh water to settle over its surface. Fresh water is less dense than salt water and tends to float on top of it, creating stratification. This surface layer could be cooled to the freezing point more easily than saltier water, facilitating the formation of sea ice. Once sea ice began to form and persist year-round, it created a feedback loop. The bright white ice reflected sunlight back to space, cooling the region further and allowing more ice to form. In this cold Arctic environment, a type of sea plant called azolla, small floating ferns, spread widely. Azolla is remarkable for its ability to grow extremely rapidly and to fix nitrogen from the atmosphere in partnership with symbiotic cyanobacteria. During the azolla event around 49 million years ago, massive blooms of this plant covered large areas of the Arctic Ocean. When the plants died, they sank to the bottom, carrying with them the carbon they had absorbed from the atmosphere through photosynthesis. In just a year, azolla can sequester as much as 6 tons of carbon dioxide per acre of coverage. Thick deposits of organic matter accumulated on the Arctic Ocean floor, effectively removing vast amounts of carbon from the atmosphere and contributing to global cooling. Meanwhile, far to the south, other tectonic changes were setting up conditions for Antarctic glaciation. The Indian subcontinent's northward journey culminated in its collision with Asia beginning around 50 million years ago. This collision, which continues today, has produced the most dramatic mountain-building episode of recent geological history. The Himalayan mountains rose up, thrust skyward by the immense compressive forces generated when two continental plates meet. Along with the Himalayas, the vast Tibetan Plateau was elevated, creating a highland region with an average elevation of more than 4,000 meters, covering an area of approximately 2.5 million square kilometers, nearly a million square miles. These massive highlands had profound effects on climate through several mechanisms. First, their presence altered atmospheric circulation patterns. affecting the development and intensity of the Asian monsoon system and steering weather patterns across much of the northern hemisphere. Second, and perhaps even more importantly, the exposure of vast areas of fresh rock surface accelerated chemical weathering processes. Weathering occurs when rainwater, which is naturally slightly acidic because it contains dissolved carbon dioxide, falls on exposed rock and reacts with minerals, particularly silicate minerals. Through a series of chemical reactions, carbon dioxide from the atmosphere is converted into dissolved bicarbonate ions, which are carried by rivers to the ocean, where marine organisms eventually incorporate them into calcium carbonate shells and skeletons that sink to the seafloor, effectively removing the carbon from the active carbon cycle for millions of years. This weathering process naturally regulates atmospheric carbon dioxide over geological timescales, but the rate of weathering depends on several factors, including temperature, precipitation, and the amount of exposed rock surface. The uplift of the Himalayas in Tibet dramatically increased the land area available for weathering and placed it in regions with heavy monsoon rainfall. As rainfall interacting with exposed rock drew more and more carbon dioxide from the atmosphere, global temperatures steadily dropped over millions of years. This is sometimes called the weathering hypothesis for Cenozoic cooling, and while other factors also played roles, the evidence suggests that increased weathering associated with Himalayan uplift was indeed a major driver of the transition from the greenhouse climate of the early Cenozoic to the icehouse climate of more recent times, by around 34 million years ago. At the boundary between the Eocene and Oligocene epochs, cooling had progressed to the point where ice began to accumulate on Antarctica. This was facilitated by another tectonic development, the separation of South America from Antarctica. As these continents drifted apart, they opened the Drake Passage, the gap that now separates southern South America from the Antarctic Peninsula. The opening of this passage, probably around 30 million years ago, allowed the development of the Antarctic Circumpolar Current, a powerful ocean current that flows eastward around Antarctica, isolating the continent from the warmer waters to the north. Currents swirling around the continent in this ring prevented warm, tropical, and subtropical water from reaching Antarctic shores, while cold water generated around Antarctica was similarly prevented from flowing northward. This thermal isolation allowed Antarctica to become progressively colder, and once temperatures fell below critical thresholds, ice began to accumulate in the continent's interior. In time, with temperatures and carbon dioxide levels continuing to fall, CO2 dropped from over 1,000 parts per million in the Eocene to perhaps 400 parts per million by the late Miocene. Around 10 million years ago, the door was open for a more subtle but remarkably regular climate driver to begin exerting its influence. This driver would orchestrate the rhythmic advance and retreat of ice sheets that characterizes the Quaternary Ice Age, the Milankovitch cycles. The story of ice ages took a major step forward in understanding thanks to the work of Milankovic, a Serbian mathematician, astronomer, and geophysicist who worked in the early 20th century. Milankovic didn't discover the idea that Earth's orbital variations might affect climate. Others had proposed this before him, but he was the first to calculate these variations precisely and to develop a comprehensive mathematical theory of how they would affect the distribution of solar radiation reaching Earth's surface. His work, compiled in his 1941 book, Canon of Insulation and the Ice Age Problem, laid the foundation for our modern understanding of the pacing of glacial cycles. Milankovic identified three aspects of Earth's orbital motion that vary in regular, predictable ways over thousands of years. First, the shape of Earth's orbit around the Sun changes from more circular to more elliptical and back again in a cycle lasting approximately 100,000 years. This variation is called eccentricity. When the orbit is more elliptical, Earth's distance from the Sun varies more over the course of a year, and this affects the total annual solar energy received, though the effect is relatively small, only about a 1% variation in total annual energy. Second, the tilt of Earth's rotational axis angle between the axis and a line perpendicular to Earth's orbital plane varies between about 22.1 and 24.5 degrees over a cycle of approximately 41,000 years. Currently, the tilt, also called obliquity, is about 23.4 degrees and is decreasing. This tilt is responsible for the seasons. When the northern hemisphere is tilted toward the Sun, it experiences summer, while the southern hemisphere, tilted away, experiences winter, and vice versa 6 months later. When the tilt is greater, seasonal contrasts are stronger, summers are warmer, and winters are colder. When the tilt is smaller, seasonal contrasts are reduced. Third, the direction that Earth's axis points in space changes over time, slowly, tracing out a circle against the background stars in a cycle lasting about 26,000 years. This motion is called precession, and it's similar to the wobbling of a spinning top. Precession determines which season occurs when Earth is closest to or farthest from the Sun in its elliptical orbit. Currently, Earth is closest to the Sun, At perihelion, in early January, during Northern Hemisphere winter, which slightly moderates the contrast between seasons in the Northern Hemisphere while enhancing it in the Southern Hemisphere. About 11,000 years ago, the situation was reversed, with perihelion occurring during Northern Hemisphere summer, making northern summers slightly warmer and winters slightly colder than they are today. Milankovic calculated how these three cycles, operating together, would affect the amount and seasonal distribution of solar radiation reaching different latitudes on Earth. He recognized that summer insolation, incoming solar radiation at high northern latitudes, was particularly important for ice ages. When summer insolation in the far north is high, it can melt the previous winter's snow, preventing accumulation. When summer insolation is low, snow persists through summer and accumulates year after year, allowing ice sheets to grow. His calculations showed that variations in Earth's orbit could indeed produce significant changes in high latitude. Summer insolation in the order of 10% or more. However, there was a puzzle. The changes in solar radiation caused by orbital variations are relatively modest, not nearly strong enough by themselves to explain the large temperature swings and massive ice sheet growth that characterize glacial cycles. Temperatures during glacial periods were about 5 to 6 degrees Celsius colder globally than during interglacials, with even larger regional differences. Ice sheets, kilometers thick, covered large portions of North America and Europe. Sea level fell by more than 100 meters. Clearly, something was amplifying the orbital signal. The answer lies in feedback mechanisms within Earth's climate system. What the Milankovic cycles do is get the ball rolling. They provide the initial push that triggers much larger changes. Consider the sequence of events during the transition into a glacial period. A decrease in solar energy hitting the Arctic due to orbital configuration allows sea ice to form during winter and, crucially, to remain through the following summer. This persistent ice reflects more solar energy back to space than open ocean water or snow-free land would, creating a positive feedback loop. The more ice, the more reflection, the cooler the climate. The more ice can form. As the climate cools, the ocean's capacity to store carbon dioxide increases. Cold water can dissolve more CO2 than warm water. So as ocean temperatures drop, the oceans absorb CO2 from the atmosphere, reducing the greenhouse effect and causing further cooling. Additionally, as ice sheets grow on land, they remove water from the ocean, causing sea level to fall. This exposes more continental shelf area, allowing more organic carbon burial and weathering to occur. Changes in ocean circulation driven by alterations in temperature, salinity, and sea ice extent can reduce the transport of heat from tropical to polar regions, enhancing cooling in high latitudes. Changes in vegetation patterns, with forests retreating and being replaced by tundra or ice, alter both albedo and the cycling of carbon and moisture. Cloud cover patterns may change, with complex effects on both incoming solar radiation and outgoing terrestrial radiation. Dust blown from expanding desert regions and from the edges of ice sheets may affect both atmospheric chemistry and the reflectivity of snow and ice when the dust settles on them. These feedback mechanisms work in both directions. Conversely, when orbital configuration favors increased solar energy in northern summers, ice begins to melt. The darker surfaces exposed by melting absorb more solar energy, accelerating the warming. As ocean temperatures rise, they release dissolved carbon dioxide back into the atmosphere. The oceans exhale CO2, strengthening the greenhouse effect. Forests expand northward, replacing tundra, and their darker surfaces absorb more sunlight than the reflective snow-covered tundra did. The climate system has a kind of momentum. Once it starts moving in one direction, feedbacks amplify the change until eventually a new equilibrium is reached, or until changes in orbital forcing begin to push in the opposite direction. This combination of orbital pacing and feedback amplification explains the dominant 100,000-year cycle of glaciation that has characterized the past million years or so. It explains why, despite the astronomical forcing being relatively weak, the climate response is so strong, and it shows why, with so many factors at play, each swing of the climate pendulum has produced its own unique conditions. The boundary conditions, ocean chemistry, atmospheric composition, ice sheet size and configuration are always somewhat different. So the response to similar orbital forcing varies from one cycle to the next. Some glacial periods are more severe than others. Some interglacial periods, like the Eemian, are warmer than the present Holocene. The details matter. Lessons from the Eemian 1. Interglacial period has become a particular focus of research, because it may offer insights into what could happen if current warming continues. This is the Eemian interglacial, also known as marine isotope stage 5 east, which occurred approximately from 130,000 to 115,000 years ago. The Eemian was the last interglacial before the most recent glacial period, which was interrupted by our current interglacial, the Holocene. What makes the Eemian particularly interesting is that global average temperatures during at least part of this period appear to have been somewhat similar to or only slightly warmer than today. And yet polar regions were considerably warmer than they are now, and sea levels were significantly higher than at present. The Eemian occurred at a time when atmospheric carbon dioxide concentrations were at pre-industrial levels around 280 parts per million, and global average temperatures had risen only modestly above those of the preceding glacial period. There was no human influence on climate. The warming was driven by natural factors, particularly the orbital configuration, which delivered relatively high solar energy to northern high latitudes during summer. This enhanced summer insolation was especially effective at melting ice and warming the Arctic region. The effects of this orbital configuration were amplified by feedback mechanisms. As Arctic sea ice melted back, exposing darker ocean water, more solar energy was absorbed rather than reflected. As temperatures rose, forests advanced northward into regions that had been tundra. The darker forest canopy absorbed more sunlight than reflective snow-covered tundra. These changes created an enhanced warming in the Arctica, phenomenon similar to the Arctic amplification we're observing today, though driven by different initial causes. Temperature reconstructions suggest that peak Eemian temperatures in the Arctic were perhaps 5 to 8 degrees Celsius warmer than pre-industrial values, and possibly several degrees warmer than today's Arctic temperatures in some regions. This Arctic warmth had consequences for ice sheets. The big question researchers have been asking is, how much did the Greenland and Antarctic ice sheets melt during the Eemian? And what does this tell us about their vulnerability to warming? The answer has profound implications for predicting future sea level rise, because the Eemian serves as a natural experiment, a case study of how polar ice responds to warmth comparable to, or perhaps, somewhat less than what we might experience this century and beyond. There is still uncertainty about exactly how much these changes affected sea levels during the Eemian, but the estimates are sobering. Multiple lines of evidence point to sea levels during the Eemian peak that were substantially higher than today. Estimates have varied over the years as more data has been gathered and analyzed, but recent research suggests sea levels may have been anywhere from 5 to 9 meters above present levels. Some studies suggest peaks might have reached even higher, though these higher estimates remain more controversial. To put this in perspective, a 6-meter sea level rise would inundate vast coastal areas worldwide. 9 meters would be absolutely catastrophic for modern civilization, affecting virtually every coastal city and low-lying region on Earth. The evidence for these elevated sea levels comes from several sources. Ancient coral reefs are perhaps the most valuable indicators. Corals are marine organisms that build hard calcium carbonate skeletons, and many coral species grow in shallow water near the ocean surface. They grow upward and outward, but they cannot grow far above the water surface. So ancient coral reefs essentially mark the position of past sea levels. Fossil coral reefs from the Eemian have been found at various locations around the world, now preserved at elevations several meters above modern sea level. By carefully dating these reefs using uranium-thorium dating and other techniques, and by accounting for geological processes that might have raised or lowered the land since the reefs formed, scientists can reconstruct past sea levels. Beach deposits and wave-cut notches carved into coastal rock formations provide additional evidence. Ancient shoreline features from the Eemian can be identified and mapped, showing where the ocean's edge once stood. In some locations, these features are now well above the current high tide line. Chemical and biological signatures preserved in sediment cores from coastal and marine environments also provide clues about past sea levels and water depths. By combining all these different types of evidence and carefully accounting for subsequent land movement due to tectonic processes and glacial isostatic adjustment, researchers have built up a picture of Eemian sea levels. One particularly important set of data comes from the Australian coast, where relative tectonic stability and good preservation of ancient reef systems have allowed detailed reconstructions. A recent study published in the prestigious journal Nature examined these Australian reefs along with data from other locations. The researchers found that sea levels remained relatively stable for most of the Eemian interglacial, at approximately 3 to 4 meters above present-day levels. This in itself is concerning, indicating that even this moderate level of warmth with Arctic temperatures, perhaps similar to, or slightly warmer than what we're approaching now, was sufficient to reduce polar ice significantly. If we were to stabilize at sea levels 3 to 4 meters above present, it would still represent an extraordinary disaster, flooding major cities, displacing hundreds of millions of people, and destroying vast amounts of infrastructure and productive land. But the story doesn't end there. The Nature study revealed something even more alarming. The authors found that in the last few thousand years of the Eemian period, Starting around 118,000 years ago, sea levels suddenly shot upward much more rapidly, reaching peaks of approximately 9 meters, or possibly even higher, above today's levels. This wasn't a gradual rise, it appears to have been a relatively abrupt jump occurring over perhaps just a few centuries or millennia, which is extremely rapid in geological terms. The authors concluded that during this phase, a critical ice sheet stability threshold was crossed, resulting in what they termed the catastrophic collapse of polar ice sheets. What could cause such a sudden acceleration in ice loss? The most likely explanation involves the marine-based portions of ice sheet areas, where ice sheets rest on bedrock that lies below sea level. Both Greenland and especially Antarctica have large marine-based sectors. The West Antarctic ice sheet, in particular, is almost entirely marine-based, resting on bedrock that in many places lies more than 2 kilometers below sea level. These marine ice sheets have a particular vulnerability. They can become unstable and collapse rapidly once certain conditions are met. The mechanism works like this. As climate warms and ocean temperatures rise, warm water can penetrate beneath floating ice shelves, extensions of ice sheets that spread out over the ocean. This warm water melts the ice shelves from below, thinning them. Ice shelves themselves don't contribute directly to sea level rise since they're already floating, but they serve a crucial function. They buttress the ice sheets behind them, holding back the flow of land-based ice toward the sea. When ice shelves thin or break up, they lose this buttressing effect, and the glaciers feeding them can accelerate dramatically. Additionally, there's a phenomenon called marine ice sheet instability. For glaciers resting on bedrock below sea level, if the grounding line, the point where the ice lifts off the bedrock and begins to float, retreats into deeper water, the ice at the grounding line becomes thicker, and thicker ice can flow faster. This faster flow draws down more ice from upstream, which increases the flow even more. The result can be a runaway process where the grounding line retreats rapidly and irreversibly, draining vast quantities of ice into the ocean over timescales of centuries rather than millennia. Once such a process begins, it may be impossible to stop even if temperatures stabilize or decrease. The Imean evidence suggests that something like this happened around 118,000 years ago. Perhaps ongoing warmth over many thousands of years gradually weakened ice shelves and thinned coastal margins of ice sheets until a critical threshold was crossed. At that point, the West Antarctic ice sheet and possibly sectors of the East Antarctic ice sheet or Greenland underwent accelerated collapse, rapidly dumping enough ice into the ocean to raise sea levels by several additional meters. This interpretation remains somewhat speculative. We can't yet say with absolute certainty which ice sheets contributed how much to the Imean sea level rise, but it's consistent with the evidence, and with our understanding of ice sheet physics. The implications for the future are profoundly unsettling. The Imean occurred with carbon dioxide levels and global average temperatures, not dramatically different from today, or from what we'll likely see later this century. Yet it resulted in sea levels meters higher than present. This suggests that we may already be committed to significant sea level rise even if we could somehow stabilize temperatures at current levels, which we're not on track to do. More likely, temperatures will continue to rise for decades at least, possibly exceeding Imean warmth, and if there's a threshold beyond which ice sheet collapse becomes inevitable, we could be approaching, or might have already passed it. This doesn't mean catastrophic sea level rise will happen immediately. The Imean warm period lasted for many thousands of years, and the major pulse of sea level rise occurred quite late in the ice sheets are massive, and even when they're losing mass, the process typically unfolds over centuries to millennia. But the key word is typically. We now know that under some circumstances, ice sheets can respond much more rapidly than once thought, and once major ice loss begins, it may prove impossible to reverse, at least on timescales relevant to human civilization. Eyes on the ice. Modern monitoring. Given these stakes, the intensive modern monitoring of Earth's ice becomes not just scientifically interesting, but absolutely essential for planning and policymaking. We need to know how fast ice is melting, which regions are most vulnerable, and whether we're seeing signs of accelerating change that might indicate approaching thresholds. Fortunately, the past few decades have seen revolutionary advances in our ability to observe Earth's cryosphere. Satellites have proven particularly valuable because they can cover vast, remote regions that would be impossible to monitor comprehensively from the ground. Different satellite sensors provide complementary types of information. Radar satellites can measure ice motion by detecting subtle changes in surface features between repeat observations. Synthetic aperture radar can even penetrate through clouds and operate in darkness, essential for monitoring polar regions where clouds are common and where the sun doesn't rise at all during winter months. Modern satellite radar mapping has revealed the flow of ice from the interior of Greenland with extraordinary detail. The ice doesn't sit static, it moves, flowing outward from the high central plateau toward the coasts under its own weight. This flow is not uniform, it's channeled by the underlying topography into distinct streams that move at different rates. In the eastern part of the island, glaciers push slowly through complex coastal terrain, navigating around mountains and through valleys carved over millions of years. In areas of higher snowfall in the northwest and west, where more ice accumulates each year, the ice speeds up by a factor of 10 or more compared to the sluggish flow in the interior. Asterisk, the ice motion maps show a landscape, or rather, an ice-scape of remarkable complexity. The ice sheet is not a simple dome, but a dynamic system with fast-flowing outlet glaciers draining distinct catchment basins. Some glaciers flow at rates of only meters per year. Others move hundreds of meters or even several kilometers per year. The fastest-moving glaciers are like rivers of ice, though rivers that flow, not in days or weeks, but over years and decades. Understanding this flow is crucial because changes in ice velocity are one of the first signs that an ice sheet is responding to changing conditions. Asterisk, the landscape beneath the ice has also been mapped using ice-penetrating radar. Aircraft equipped with radar systems fly back and forth across Greenland, sending radio waves down through the ice. These waves reflect off the bedrock beneath, and by measuring the time delay, scientists can determine the ice thickness. Thousands of flight lines have now been flown, revealing the hidden topography of Greenland's bedrock in unprecedented detail. This revealed some surprises, including a massive canyon system that extends from the center of the island northward to the coast. Asterisk, this canyon, discovered through analysis of radar data, is truly enormous by any standard, approximately 750 kilometers long in total extent. Though the main channel is about 550 kilometers, in places it reaches 800 meters deeper than the Grand Canyon. In many sections and up to 10 kilometers wide, this ancient river valley, carved before Greenland was covered by ice, was completely hidden beneath kilometers of ice until radar allowed us to see through to the bedrock. The canyon may once have served as a major drainage route for the interior of Greenland during warmer periods, channeling meltwater to the ocean. Understanding such features is important because subglacial topography influences how ice flows and how it might respond to warming. Asterisk, modern satellite monitoring has allowed scientists to track dramatic events at Greenland's glaciers. One of the most volatile is the Petermann Glacier in northwestern Greenland. This glacier has been the site of some spectacular calving events, instances where large pieces of ice break off from the glacier's front and float away as icebergs. Amid unusually warm summer temperatures in 2012, satellites tracked giant iceberg as it broke off from Petermann's floating ice tongue and moved down the glacier's outlet channel. Asterisk, the iceberg that calved in 2012 was approximately 130 square kilometers in area, an island of ice about twice the size of Manhattan. Despite its enormous size, this piece of ice stayed together as a coherent block for quite some time, drifting slowly through the channel between Greenland and Ellesmere Island. After about 2 months of monitoring, it finally began to fragment into smaller pieces. These large calving events from Petermann have occurred multiple times in recent years. Major calvings happened in 2010, 2012, and 2017, each removing substantial portions of the glacier's ice shelf, while the ice shelf was already floating and thus didn't directly raise sea level when it broke off. The loss of this ice has likely reduced the buttressing effect on the glacier behind it, potentially allowing the glacier to speed up and deliver more ice to the ocean. Asterisk, another closely watched glacier is Jakobshovn Isbrae, on Greenland's west coast, often cited as the fastest flowing glacier in the world. Jakobshovn flows toward the sea at a rapid rate that has varied over time but has reached 40 meters per day or more during its fastest periods. That's about 14 kilometers per year. To put that in perspective, you could watch this glacier flow if you had the patience to observe it carefully for several hours. At the ice front, where the glacier meets the sea, Jakobshovn has been retreating dramatically. Historical maps and photographs show this retreat clearly. In 1851, when the glacier's position was first accurately mapped by explorers, the ice front was located at the mouth of the long fjord through which the glacier flows. Over the following 150 years, the front gradually retreated up the fjord, but the retreat accelerated dramatically starting in the late 1990s. By the early 21st century, Jakobshovn was retreating at unprecedented rates, and the glacier was thinning rapidly. The front has now retreated approximately 50 kilometers from its 1851 position, and the glacier is dumping enormous quantities of ice into the ocean by some estimates, about 35 cubic kilometers per year, making it one of the single largest contributors to sea level rise from Greenland. Why has Jakobshovn retreated so dramatically? Research has identified several factors. One is that water seeping down through cracks and crevasses in the glacier's surface is reaching its base, where it acts like a lubricant, reducing friction between the ice and the bedrock and allowing the ice to slide faster. This is called basal sliding, and it can significantly enhance ice flow. But perhaps even more important is what's happening at the glacier's terminus where it enters the ocean. Jakobshavn's ice flows into a fjord where it comes into contact with seawater. Asterisk, for many years, A floating ice tongue extended from the glacier out into the fjord, and this ice tongue was buttressed by the fjord walls and by pressure from ice behind it, creating a relatively stable configuration. But in the 1990s, warmer ocean waters began penetrating the fjord, reaching the glacier's terminus. These warmer waters only a few degrees Celsius above freezing, but substantially warmer than the ice melted the floating ice tongue from below and at the sides. As the ice tongue thinned and weakened, it lost its buttressing effect. Eventually, much of it broke up and floated away. Asterisk without the restraining effect of the ice tongue. The glacier behind it accelerated dramatically. Freed from this constraint, ice from farther inland could flow faster toward the sea. As the ice flowed faster, the surface of the glacier lowered, it thinned. This thinning propagated inland, affecting ice many kilometers from the coast. The glacier is now in a state where it's pouring ice into the ocean at a rate that far exceeds the rate at which snow accumulates in its catchment area. Unless this imbalance is reversed, the glacier will continue shrinking. Similar dynamics are playing out at glaciers around Greenland and, as we'll see, at ice shelves and glaciers in Antarctica. The interaction between ice and warming ocean water is one of the most important processes driving current ice loss. And it's an area of intense research because ice sheet models need to accurately represent these processes in order to make reliable projections of future sea level rise. To quantify the overall rate of ice loss, scientists use measurements from the GRACE satellites, the Gravity Recovery and Climate Experiment. These satellites don't observe ice directly, but instead measure tiny variations in Earth's gravitational field. The principle is clever. Mass attracts mass through gravity, so regions with more mass pull slightly harder on orbiting satellites. By precisely measuring the distance between two satellites as they orbit Earth in formation, scientists can detect minute changes in their relative velocity caused by passing over regions of greater or lesser mass. When ice sheets lose mass, the gravitational pull of that region decreases slightly, and GRACE can detect this change. Analysis of GRACE data from 2003 to 2009 showed that Greenland lost approximately 1 trillion tons of ice, about 1,000 cubic kilometers of ice, enough to raise global sea level by nearly 3 millimeters. The mass loss was concentrated along the island's coastlines, particularly in the northwest, west, and southeast, where major outlet glaciers are located. Follow-up studies looking at longer time periods have found that the rate of ice loss has varied from year to year, but has generally continued and may have accelerated. Some recent estimates suggest Greenland is now losing more than 250 cubic kilometers of ice per year, though there's year-to-year variability depending on weather patterns, summer temperatures, and other factors. This numbered rate of ice loss from Greenland mirrors trends in the Arctic as a whole. Arctic sea ice has undergone dramatic decline over the period of satellite observations, which began in 1979. By September 2012, summer sea ice coverage had fallen to just 3.4 million square kilometers, about half of the average for the 1980s and early 1990s. This was a shocking record low. While the ice rebounded somewhat in subsequent years, 2013 and 2014 saw more ice than 2012, the coverage remained well below the long-term average. Subsequent years have seen continued low extents, with 2020 and 2019 ranking as the second and third lowest on record after 2012. The decline isn't just in area, but also in thickness. The Arctic Ocean once contained substantial amounts of thick, multi-year ice that had survived several summer melt seasons and had grown to thicknesses of 3 meters or more. This old thick ice is now rare. Much of the Arctic is covered by thinner, first-year ice that forms in winter and melts back extensively in summer. Thinner ice is more vulnerable to melting and to being pushed around by winds and currents, creating more dynamic and unpredictable ice conditions. Analyzing global data from the GRACE mission over a longer period. One comprehensive study calculated that Earth as a whole lost approximately 4,000 cubic kilometers of ice in the decade leading up to 2012. That's about 400 cubic kilometers per year on average. Though the rate was not constant over this period, this ice loss came from multiple sources: Greenland, Antarctica, mountain glaciers in the Alps, Andes, Himalayas, Alaska, and other regions, and from changes in groundwater and other terrestrial water storage. The fact that ice loss is occurring worldwide, not just in one region, is strong evidence that a global warming signal is responsible. The implications for sea level rise are significant. Sea levels around the world are now expected to rise by approximately 1 meter, perhaps somewhat more, perhaps somewhat less, depending on future emissions and ice sheet behavior by the end of the 21st century. A 1 meter rise is enough to dramatically increase the frequency and severity of coastal flooding, to threaten low-lying islands and coastal communities, to contaminate coastal freshwater aquifers with saltwater, and to cause substantial economic losses. But this projection is for just the next 80 years. What will happen beyond that, over the next several centuries, depends critically on understanding ice sheet dynamics and on the choices humanity makes about greenhouse gas emissions in the coming decades. Drilling into history to gauge the resilience of Greenland's great ice sheet and to understand how it has responded to past warm periods. Scientists mounted one of the most intensive glacial drilling projects to date. This was the North Greenland Eemian Ice Drilling Project. Known by its acronym NEAM, the goal was ambitious: to drill through the ice sheet to bedrock, extracting a continuous core that would capture a complete record of ice accumulation over more than 100,000 years, including the crucial Eemian interglacial period. Ice core drilling is a remarkable technological achievement. The drill site for NEAM was located in northwest Greenland at 77.45 degrees north latitude, on the ice sheet's high plateau at an elevation of approximately 2,450 meters. Here, the ice is about 2,540 meters thick, representing over 130,000 years of accumulated snowfall. The drilling operation required extensive logistics, equipment, fuel, food, and supplies had to be flown in during the brief Arctic summer. A camp was established on the ice, with heated buildings for the drill operation, laboratories for immediate ice core analysis, and living quarters for the international team of scientists and technicians. The drilling itself is a slow, painstaking process. A hollow drill with cutting teeth on the bottom is lowered down the borehole on a cable. The drill rotates, cutting a cylindrical core of ice that is captured inside the hollow drill tube. After drilling a section typically a few meters at a time, the drill is pulled back to the surface. The core is extracted, and the process repeats. As the hole gets deeper, the time for each cycle increases since the drill must travel farther up and down. At the NEAM site, it took multiple years of drilling during summer seasons to reach the bedrock. The ice cores brought to the surface are carefully handled and documented. They're examined immediately for visible features layers, bubbles, ash deposits from volcanic eruptions, and other characteristics. They're then cut into sections for different types of analysis. Some sections are melted to measure the chemical composition of the water and any dissolved substances. Some are kept frozen for analysis of gases trapped in tiny bubbles within the ice. These bubbles are samples of ancient atmosphere, allowing us to measure past carbon dioxide, methane, and other gas concentrations. Some sections are analyzed for isotopic composition, which serves as a temperature proxy. The isotopic analysis is based on the fact that water molecules can be made of different isotopes of hydrogen and oxygen. The most common form has normal hydrogen 1H and oxygen 16160, but some water molecules contain deuterium-heavy hydrogen, 2H, or oxygen 1818. The ratio of these isotopes in precipitation depends on temperature. Colder conditions lead to snow that's depleted in the heavier isotopes. By measuring isotope ratios in ice core samples and calibrating against known temperatures, scientists can reconstruct past temperature changes with remarkable precision. The NEAM ice core's most exciting section was the ice deposited during the Eemian. This ice came from depths between about 2,000 and 2,400 meters, representing the period from roughly 130,000 to 115,000 years ago. The isotopic data from this section told a surprising story that has important implications for understanding Greenland's stability. If you could have been a visitor to northern Greenland during the peak of the Eemian warming, you would have stood on ice that was still over 2 kilometers thick. Temperature reconstructions showed that conditions were substantially warmer than today, about 8 degrees Celsius warmer than pre-industrial temperatures, and several degrees warmer than present-day northern Greenland. Summer temperatures likely remained above freezing for extended periods, and there would have been substantial surface melting. And yet, despite these much warmer conditions persisting for thousands of years, the ice sheet had receded by only about 25% of its volume, relatively modest amount considering the intensity and duration of the warming. The ice sheet survived. It didn't collapse. This was initially somewhat reassuring, suggesting a degree of resilience. However, the finding must be interpreted carefully. A 25% reduction in Greenland's ice volume still translates to a sea level contribution of roughly 1.5 to 2 meters, highly significant. Though not enough to account for all of the elevated Eemian sea level, this points the spotlight firmly at Antarctica, which must have contributed the majority of the Eemian sea level rise. And the NEAM core provides information only about this particular location in northern Greenland. Other parts of the ice sheet, particularly in the south where temperatures are warmer, may have experienced more dramatic thinning. Moreover, the 25% figure represents the situation in northwest Greenland specifically during the Eemian. It doesn't necessarily tell us how the ice sheet will respond to the particular pattern and rate of warming we're experiencing now, which is different from Eemian warming in several respects. The Eemian warming was driven primarily by orbital factors affecting summer insolation, whereas current warming is driven by greenhouse gases affecting the radiation balance year-round. The pace of change may also be different. The Eemian warming developed over several thousand years, while current warming is occurring over decades to centuries. Ice sheets might respond differently to rapid versus gradual forcing. Asterisk still. The NEM results have shifted the focus of concern from Greenland to Antarctica. If Greenland contributed perhaps 2 meters at most to median sea levels, but total sea levels were 6 to 9 meters higher, then Antarctica must have lost enormous quantities of ice. This has profound implications because the Antarctic ice sheet contains far more ice than Greenland, enough to raise sea levels by about 58 meters if it melted completely, compared to Greenland's 7 meters. If even a modest fraction of Antarctic ice is vulnerable to melting at temperatures we might reach this century or next, the long-term sea level implications are staggering. Antarctica, the sleeping giant. Antarctica, Earth's southernmost continent, is a frozen realm of almost unimaginable scale. It contains approximately 90% of all the ice on Earth and about 70% of all the planet's fresh water, locked in ice sheets averaging nearly 2 kilometers thick. The continent itself is larger than Europe, covering about 14 million square kilometers. In winter, when sea ice forms around its edges, the frozen area more than doubles. Antarctica is also the highest continent, with an average elevation of about 2,500 meters, not because the bedrock is particularly elevated, but because so much ice has piled up on top of it. Asterisk, this is a continent of extremes, the coldest, driest, windiest, and most remote place on Earth. The Russian research station, Vost, located near the center of East Antarctica, holds the record for the lowest naturally occurring temperature ever measured on Earth's surface, minus 89.2 degrees Celsius, minus 128.6 degrees Fahrenheit, recorded in July 1983. More recently, satellite sensors have detected even colder temperatures in pockets of the East Antarctic interior, reaching below minus 93 degrees Celsius. These are temperatures at which carbon dioxide freezes solid, where exposed skin would freeze almost instantly, where most materials become brittle and fragile. Asterisk, despite these brutal conditions, scientists maintain a presence on the continent, operating dozens of research stations and conducting fieldwork, even in the austral winter, when darkness prevails for months. The questions they're investigating are critical. How is Antarctica responding to climate change? And how will it respond in the future? The answers matter immensely because of the sheer volume of ice involved. Every meter of average thickness lost from Antarctic ice sheets translates to roughly 14 million cubic kilometers of water entering the ocean. Even small percentage changes in Antarctic ice volume can profoundly affect global sea levels. Asterisk, data from satellites and field observations show that Antarctica overall has, until recently, been in a complex state regarding mass balance. Some areas have been gaining mass as increased snowfall, a paradoxical consequence of warming. Since warmer air can hold more moisture and thus deliver more precipitation, ADS ice, to the interior plateau. Other areas, particularly along the coast, have been losing mass as glaciers speed up and ice shelves thin. When the gains and losses are summed up, the continent as a whole has been losing mass, but the net loss rate has varied considerably over time. Asterisk, the vast plateau of Antarctic ice that dominates the eastern and central parts of the continent is indeed one of the driest deserts on Earth in terms of precipitation. Some interior regions receive less than 50 millimeters of water equivalent per year, less than the Sahara Desert. What little snow falls tends to remain indefinitely, adding microscopic layers to the ice sheet year after year, century after century, millennium after millennium. You can see evidence of this steady accumulation at the Amundsen-Scott South Pole Station, located precisely at the geographic South Pole. Asterisk, the station's geodesic dome, built in the 1970s as the main facility, provides a dramatic illustration of snow accumulation rates. When the dome was constructed, its entrance was at snow surface level. Over the subsequent decades, as snow accumulated, the entrance had to be repeatedly excavated. By the time the dome was decommissioned in 2009, replaced by a new elevated station building, designed to avoid the snow burial problem, the original entrance was nearly buried under approximately 10 meters of compacted snow. The dome structure itself was in danger of being crushed by the weight of accumulating snow on its roof. This burial occurred in just about 35 years, illustrating the relentless, steady accumulation that builds ice sheets over geological timescales. Asterisk, with a thickness of up to more than 4 kilometers in places. The ice sitting atop the stable East Antarctic craton, the ancient continental bedrock, forming the core of East Antarctica, will not melt easily. This is reassuring in some respects. The East Antarctic ice sheet is thought to be relatively stable, at least in its central portions. Because of several factors, the bedrock beneath it is above sea level in most areas, reducing vulnerability to marine ice sheet instability. Temperatures are extraordinarily cold, so even substantial warming would leave much of the region well below freezing, and the interior is so remote from ocean influences that warming is transmitted there only slowly. However, this stability assessment is truer for some parts of Antarctica than others. The continent is not a uniform mass of ice resting on a uniform foundation. Instead, it consists of distinct regions with very different characteristics. The distinction between East and West Antarctica is fundamental. East Antarctica, the larger portion that includes the South Pole and extends toward the Indian Ocean, is indeed built on a stable continental foundation, but West Antarctica, extending toward South America and the Pacific Ocean, tells a very different story. Asterisk, this dramatic difference in geology has been revealed through an extraordinary technological achievement, ice-penetrating radar, mapping of the entire continent. Using techniques similar to those employed in Greenland but on a much larger scale, research aircraft equipped with radar systems have flown millions of kilometers of survey lines across Antarctica over several decades. The radar waves penetrate through the ice, sometimes through more than 4 kilometers of ice and reflect off the bedrock, allowing scientists to map the hidden topography of the continent. Beneath the ice, asterisk, the resulting maps show a two-sided continent. The eastern part, the portion of Antarctica that would lie primarily in the eastern hemisphere if we extended longitude lines to the South Pole, rests on a foundation of continental crust that is largely above sea level. This is geologically similar to other continents, a thick, relatively light granitic crust that floats high on the denser mantle rocks below. But western Antarctica presents a starkly different picture. Much of the bedrock in West Antarctica lies below current sea level in some areas, more than 2,500 meters below sea level. In fact, without the ice, much of West Antarctica would be an archipelago of islands, surrounded by ocean, rather than a continuous landmass. Asterisk, this matters because ice resting on bedrock below sea level is inherently less stable than ice on bedrock above sea level, for reasons related to the marine ice sheet instability we discussed earlier. Along Antarctica's coast, particularly along the Amundsen Sea sector of West Antarctica, ice has been disappearing at an accelerating rate. This region includes some of the most rapidly changing glaciers on Earth, and it has become ground zero for concerns about Antarctic ice sheet stability. Asterisk, satellite observations using radar technique that can detect ice motion and changes in elevation with extraordinary precision. Inland ice streams moving toward the ocean at speeds of at least 100 meters per year, with some glaciers moving several times faster. These ice streams are the arteries through which Antarctica delivers ice to the ocean. They funnel ice from vast catchment areas in the interior toward the coast, where the ice either melts or calves off as icebergs. The ice streams end up feeding into floating ice shelves that extend hundreds of kilometers from the grounded ice sheet out over the ocean. Asterisk, ice shelves are fascinating features. They're extensions of ice sheets that spread out over the ocean while remaining attached to the ice on land. Because ice is less dense than water, it floats, but the ice shelf is constantly being fed by ice flowing from inland, and it also gains mass from snowfall on its surface. At the same time, ice shelves lose mass through melting at their base, where they contact seawater, through melting or sublimation at their surface, and through the calving of icebergs from their outer edges. When these processes balance, an ice shelf maintains a relatively stable size. When loss exceeds supply, the shelf thins and retreats. Asterisk, one glacier that has become emblematic of Antarctic change is the Pine Island Glacier, a major outlet draining a large sector of the West Antarctic ice sheet into the Amundsen Sea. This region is the greatest source of uncertainty in current projections of global sea level rise. Pine Island Glacier alone drains about 10% of the entire West Antarctic ice sheet, and its catchment area contains enough ice to raise global sea level by about 1.7 meters. The glacier and its floating ice shelf have been the focus of intensive research because they appear to be undergoing rapid changes that could accelerate further. Asterisk, Pine Island's ice shelf, like other ice shelves around Antarctica, grows through the continuous delivery of ice from inland. As the shelf expands, it becomes prone to fracturing because ice, despite flowing like a very viscous fluid over long time scales, is brittle and cracks when stressed. Large cracks, or rifts, can form in ice shelves, sometimes extending for dozens of kilometers. When rifts propagate all the way through an ice shelf, large pieces break off as icebergs, a process called calving. That's natural and normal for ice shelves. A particularly dramatic example occurred when a giant crack appeared in Pine Island's ice shelf that was tracked carefully by satellites. The rift grew over time, and within about 2 years, a massive iceberg broke free. The berg, designated BT1, had an area of about 720 square kilometers, roughly the size of Singapore, or about 8 times the size of Manhattan. Satellite images captured the berg as it drifted away from the ice shelf, slowly rotating and fragmenting over subsequent months. Similar large calving events from Pine Island have occurred repeatedly in recent years. In 2013, 2015, 2017, 2018, and 2020, suggesting an accelerating pattern. Asterisk, while these calving events are dramatic and capture public attention, scientists are more concerned about what's happening beneath the surface. changes that are less visible but potentially more consequential. The waters of the Southern Ocean that swirl around Antarctica have been getting warmer in recent decades, particularly at depths of a few hundred meters, where relatively warm water masses circulate. The Amundsen Sea region has seen especially pronounced warming, with subsurface water temperatures rising at rates approaching 0.2 degrees Celsius per decade in some areas. 0.2 of a degree per decade might not sound like much, but these waters, though above freezing, are in contact with ice, and relatively small temperature differences translate to large differences in melt rates. Asterisk. This warming ocean water has a profound effect on ice shelves by melting them from below, a process largely invisible from satellite observations. Ice shelves float in equilibrium, with about 90% of their mass below the water surface. When warm water circulates beneath the shelf, it melts the ice from below, thinning the shelf without producing obvious surface features. This basal melting can be extremely effective at removing ice. In a comprehensive survey of Antarctic ice shelves using satellite altimetry and other techniques, scientists determined that basal melting was responsible for approximately 55% of all mass lost from Antarctic ice shelves between 2003 and 2008. In some regions, particularly in the Amundsen and Bellingshausen sea sectors, basal melting accounts for even larger fractions of ice loss. Asterisk. The rate of basal melting depends on ocean temperature, circulation patterns, and the geometry of the cavity between the ice shelf base and the seafloor. Where warm water can penetrate deeply beneath ice shelves, very high melt rates can occur. A team of researchers came to Pine Island Glacier to measure these processes directly, deploying instruments through the ice to monitor conditions in the ocean cavity beneath the ice shelf. This was an extraordinary technical challenge, requiring them to drill through about 500 meters of moving ice to reach the ocean below, all while operating in one of the most remote and hostile environments on Earth. Asterisk. After 5 years of preparation and planning, the team successfully installed sensors in the cavity beneath Pine Island Glacier's ice shelf. What they found was sobering. The instruments measured water temperature, salinity, ocean currents, and ice thickness at the base of the shelf. In some locations, they recorded basal melt rates of approximately 6 centimeters per day. 6 centimeters per day translates to roughly 22 meters per year, an astonishing rate of ice loss from below. Of course, melt rates vary across the ice shelf depending on local conditions, and the average is lower than these peak values. But even average melt rates of several meters per year are significant when sustained over large areas and over multiple years. Asterisk. This submarine melting matters because ice shelves, though they don't directly contribute to sea level rise while they're floating, serve a critical function in the ice sheet system. They act as buttresses, holding back the glaciers that feed them. Think of an ice shelf as a cork in a bottle, or a dam holding back a reservoir. The ice shelf experiences resistance from the ocean water around it, from contact with islands or peninsulas at its sides, and from internal stresses within the ice. This resistance is transmitted back upstream to the grounded glacier, slowing its flow toward the ocean. Asterisk. When an ice shelf thins or breaks up, this buttressing effect is reduced or eliminated. The glacier behind it, freed from this restraint, can accelerate dramatically. This is precisely what researchers have observed at Pine Island and at neighboring glaciers in the Amundsen Sea sector. As the ice shelves have thinned, the glaciers have sped up. As the glaciers have sped up, they've drawn down more ice from their catchment areas, causing the inland ice to thin. This thinning propagates upstream, potentially affecting ice hundreds of kilometers from the coast. The system is interconnected, and changes at the coast can trigger widespread consequences inland. This dynamic is thought to be responsible for one of the more puzzling aspects of recent Antarctic change, the expansion of sea ice around much of the continent even as the climate warms and land ice decreases. Antarctic sea ice extent actually increased slightly from the late 1970s through about 2015. In contrast to the dramatic decline of Arctic sea ice, this seemed paradoxical and was sometimes cited by those skeptical of climate change as evidence against warming. However, the apparent contradiction can be explained by understanding the complex interactions between ice shelves, ocean circulation, and sea ice formation. Asterisk. One possibility is that changes in wind patterns themselves related to climate change have been pushing sea ice into thicker, more extensive formations. The winds circling Antarctica in the Southern Ocean have intensified and shifted poleward, potentially spreading sea ice over a larger area even as its total volume doesn't necessarily increase. Another, perhaps more important, factor is the effect of ice shelf melting on the ocean surface layer. When ice shelves melt from below, they release fresh water into the ocean. Fresh water is less dense than salt water and tends to float on top of the saltier, deeper layers, creating a stable stratification. Asterisk. This layer of cold, fresh surface water can readily freeze, forming sea ice. In effect, the melting of Antarctica's ice shelves has spread a layer of cold, fresh water over coastal seas, facilitating sea ice formation. The sea ice then reflects, Sunlight, keeping surface waters cool and allowing more ice to form another feedback loop. This means that expanding sea ice doesn't contradict the overall warming and ice loss trend. Rather, it's a consequence of the ice sheet changes occurring at and below the waterline. It's worth noting that this sea ice expansion reversed dramatically after 2015, with Antarctic sea ice declining to record lows in subsequent years. Adding another layer of complexity to the story, to better understand what's happening beneath Antarctic ice shelves and to predict future changes. Researchers have undertaken ambitious expeditions to measure conditions in situ. The Pine Island Glacier expedition mentioned earlier is one example. Getting to these remote locations requires extensive logistical support, typically involving flights from Chile or New Zealand to Antarctic bases, then smaller aircraft to field camps on the ice, then helicopter or ground traverse to the specific research site. Once there, teams must contend with extreme cold, high winds, the risk of crevasses, and the challenges of operating sophisticated scientific equipment in harsh conditions. The drilling operation itself is an engineering challenge. Researchers used hot water, drilling pumping heated water down through a nozzle to melt a borehole through 500 meters of ice. This required generating and maintaining large volumes of hot water using fuel-powered heaters, a significant logistical undertaking in such a remote location. Once the borehole was established, instruments could be lowered into the ocean cavity beneath the ice shelf. These included temperature and salinity sensors, current meters to measure ocean flow, an upward-looking sonar to measure the ice thickness above. The measurements revealed an ocean cavity beneath the ice shelf were relatively warm, deep water that has circulated around Antarctica at depth and has temperatures above freezing was reaching the ice shelf base. This water, though only about 2 to 3 degrees Celsius above the freezing point of seawater, which is about minus 1.8 degrees Celsius, is warm enough to efficiently melt ice when it comes into contact with it. The temperature difference between this water and the ice drives rapid melting. The team found that ocean circulation patterns, influenced by winds, tides, in the shape of the seafloor and ice shelf cavity, control how much of this warm water reaches the most vulnerable parts of the ice shelf. Understanding these processes is crucial for improving ice sheet models and projections. Current ice sheet models vary considerably in how they represent ice-ocean interactions, partly because the processes are complex and partly because we lack detailed observations of conditions beneath most of Antarctica's ice shelves. The Pine Island measurements and similar work at other glaciers are helping to constrain these models, but significant uncertainties remain. This translates into large uncertainties in projections of Antarctica's contribution to future sea level rise. Projections range from tens of centimeters to more than a meter by 2100, with even greater spreads for longer-term projections. The vulnerability of current-based ice shelves to ocean warming was dramatically illustrated by events on the Antarctic Peninsula, the long mountainous finger of land that extends northward from Antarctica towards South America. This is the warmest part of the continent, experiencing temperatures that can rise above freezing in summer. Along the peninsula's eastern coast, a series of ice shelves had existed for thousands of years, each named alphabetically: Larsen A, Larsen B, Larsen B, Larsen C, and so on, extending southward. The Larsen A ice shelf, the northernmost and smallest, collapsed in 1995 over the course of a few days, disintegrating into a mass of small icebergs and ice debris. This was surprising but was somewhat dismissed as an isolated event affecting a relatively small and marginal ice shelf. However, attention then turned to Larsen B, a much larger ice shelf farther south. Larsen B had been stable since at least the end of the last ice age, approximately 12,000 years ago, and probably much longer. Studies of its structure suggested it had been in place throughout the Holocene interglacial period. But by the early 2000s, satellite observations detected troubling signs. The ice shelf was thinning. Surface meltwater was ponding in pools on the ice shelf surface during summer, a concerning sign, because surface melting can exploit and widen cracks in the ice through a process called hydroformation. When water fills a crevasse, its weight can drive the crack deeper, potentially fracturing the ice all the way through. Additionally, water at the surface is darker than snow and ice, so it absorbs more sunlight, creating a feedback that enhances melting. In early 2002, conditions reached a critical point. By late January and early February, the ice shelf began to splinter rapidly. Long cracks that had been gradually developing suddenly propagated at extraordinary speeds, in some cases kilometers per day. The massive ice shelf, which had covered about 3,250 square kilometers, an area larger than Rhode Island, broke into countless small icebergs. Satellite images captured the disintegration in dramatic fashion. On February 23, 2002, the shelf was largely intact, though heavily fractured. By March 7, just 12 days later, it had completely collapsed, forming a vast field of small icebergs and ice debris. drifting out into the Weddell Sea. The speed of the collapse shocked researchers. Previous estimates had suggested that even if Larsen B were to break up, it would take years or decades. Instead, it happened in a matter of weeks. The collapse revealed the dark ocean water beneath, creating a stark visual contrast in satellite images between the white ice and the dark water. Scientists studying the event concluded that a combination of long-term thinning from basal melting, surface melting creating meltwater ponds, and the weakening of the ice shelf's internal structure had brought it to a critical threshold. Once that threshold was crossed, the collapse proceeded rapidly and irreversibly. What happened next provided clear evidence of ice shelves' buttressing function. The glaciers that had been flowing into Larsen B glaciers with names like Hectoria, Green, and Crane suddenly accelerated. Within months of the ice shelf's collapse, these glaciers were flowing 2 to 8 times faster than before. This acceleration meant they were delivering far more ice to the ocean. Measurements showed that these glaciers together were adding approximately 27 cubic kilometers of ice to the ocean per year after the collapse. Compared to much lower rates before, this ice came from the land-based glaciers and thus did contribute directly to sea level rise. Unlike the floating ice shelf itself, the Larsen B collapse and its aftermath served as a stark warning of what could happen elsewhere. In Antarctica, if ice shelves continue to weaken and break up, while the Antarctic Peninsula is the warmest part of the continent and might be considered an exceptional case, there's no fundamental reason why similar processes couldn't affect larger ice shelves farther south if warming continues. The Ross and Ron-Felkner ice shelves, the two largest ice shelves in Antarctica, together cover an area larger than Spain. Their collapse would have profound consequences for the ice sheets behind them. Evidence from the last interglacial period. The Eemian brings an ominous warning of what could lie ahead for Antarctica. We've already discussed how Eemian sea levels were 5 to 9 meters higher than today, with a sudden pulse of rapid rise. Late in the reconstruction of this sea level history comes from studying ancient coral reefs, but particularly important work has focused on the Australian coast, where tectonic stability and good preservation allow precise reconstructions. The study published in Nature that we mentioned earlier examined coral reef terraces along the western Australian coast, combining this with data from other locations, including the Seychelles and the Red Sea. By carefully dating these reefs using uranium-thorium dating technique that can provide ADs with uncertainties of just a few thousand years for samples in this age range, and by analyzing the coral species present, which indicate water depth, the researchers reconstructed how sea level changed throughout the Eemian. Their findings showed that sea levels remained relatively stable at approximately 3 to 4 meters above present for most of the Eemian, roughly from 127,000 to 120,000 years ago. This already indicates significant ice loss from Greenland and likely from Antarctica as well, since reaching even 3 to 4 meters requires substantial melting. But then, starting around 119,000 years ago, sea levels rose rapidly to peaks of approximately 9 meters above present, possibly even reaching slightly higher in brief spikes. This rise of 5 to 6 meters in just a few thousand years represents an extraordinarily rapid addition of ice to the ocean, the authors concluded, in their careful scientific language, that a critical ice sheet stability threshold was crossed during this period, resulting in what they termed catastrophic collapse of polar ice sheets. The word catastrophic is not used lightly in scientific papers. It indicates a rapid, irreversible change with major consequences. The question is, which ice sheets collapsed? Given that Greenland appears to have been relatively stable during the Eemian, contributing perhaps 2 meters at most, the bulk of the Latimian sea level rise must have come from Antarctica. This means that at least one sector of the Antarctic ice sheet, most likely the West Antarctic ice sheet, given its marine-based nature and vulnerability, underwent rapid collapse during the late Eemian. What triggered this collapse? The timing is intriguing. The late Eemian was actually a period of cooling in some records, with orbital factors beginning to reduce summer insolation in the northern hemisphere. Yet, Antarctic ice apparently collapsed during this period. One hypothesis is that there's a lag in the system, that Antarctic ice shelves and marine ice sheets were progressively weakened by millennia of warm ocean temperatures. Earlier in the Eemian and by 119,000 years ago, critical thresholds were finally crossed even as atmospheric temperatures were beginning to decline. This would suggest that ice sheet response to warming can be significantly delayed, and that once certain thresholds are crossed, the lapse may proceed even after the initial warming trigger is removed. Another possibility involves changes in ocean circulation. The Eemian was characterized by different ocean circulation patterns than today, and changes in these patterns late in the interglacial might have brought warmer waters into contact with vulnerable ice shelves or changed the rate of basal melting. The details remain uncertain, but the overall message is clear. During a warm period roughly comparable to or slightly warmer than what we're heading toward, Antarctic ice underwent major collapse, contributing meters of sea level rise in a brief interval. Looking ahead, the uncertainties about Antarctica's future are profound. Some modeling studies suggest that under high emissions scenarios, Antarctic ice loss could contribute more than a meter to sea level rise by 2100, and several meters by 2300. Other models produce more modest projections. The spread reflects genuine scientific uncertainty about ice sheet physics, ocean circulation changes, and how these systems will respond to unprecedented warming. What's clear is that Antarctica holds the potential for very large, long-term sea level rise, and that the changes we're observing today, accelerating glaciers, thinning ice shelves, increased basal melting, may be early signs of much larger changes to come. The still unfolding story of Earth's past, revealed through ice cores, ocean sediments, coral reefs, and other geological archives, tells us about the fundamental mechanisms that shape climate over thousands and millions of years. It shows us a planet with a dynamic climate system capable of dramatic swings between icehouse and greenhouse states. It reveals the role of orbital variations in pacing glacial cycles, the powerful feedback mechanisms that amplify these orbital nudges into major climate changes, and the vulnerabilities of ice sheets to warming oceans and atmospheres. This knowledge is invaluable for understanding our current situation and for anticipating what the future might hold. But while the past provides context and reveals mechanisms, it's the unique conditions of our time that will determine the actual trajectory of sea levels, ice coverage, and temperatures in the coming centuries and millennia. We're conducting an experiment with Earth's climate that has no precise parallel in the geological past. We're adding greenhouse gases to the atmosphere at rates that may be unprecedented, or at least unmatched, since major geological catastrophes like the Paleocene, Thermomaximum Actimer. We're doing this on a planet with human civilization, infrastructure, and populations concentrated in regions that would be profoundly affected by climate change. What's at stake in the coming centuries is the world. We know the particular configuration of coastlines, climate zones, and ecosystems that has nurtured and sustained human civilization. The Earth itself will survive and continue its long evolution. Life will adapt, evolve, and diversify as it has through all of Earth's previous climate changes. But the familiar world of the Holocene, the remarkably stable interglacial period during which human civilization developed, may be transitioning to something quite different. Whether that transition is managed or chaotic, gradual or abrupt, depends critically on choices being made now and in the coming decades. The cryosphere. Earth's frozen water stands as both a witness to climate change and a potential amplifier of it. As ice melts, it reveals landscapes and seabeds that haven't seen sunlight in millennia. It releases water that raises sea levels incrementally but inexorably. It changes the planet's reflectivity, allowing more solar energy to be absorbed. It alters ocean circulation patterns that distribute heat around the globe. These changes don't occur in isolation, but interact with countless other aspects of the Earth system in ways we're still working to fully understand. Scientists continue their work, drilling deeper into ice, deploying more sophisticated sensors, developing more comprehensive models, searching ancient sediments for clues to past climates. Each research expedition, each ice core, each satellite observation adds to our understanding. International collaborations bring together experts from dozens of countries, sharing data and insights. Young researchers bring new techniques and perspectives to long-standing questions. The pace of discovery continues to accelerate, driven by improving technology and by the urgency of the questions being asked. Yet significant uncertainties remain. We don't know exactly when critical thresholds might be crossed, beyond which ice loss becomes rapid and irreversible. We don't know precisely how much warming would commit us to eventual complete loss of the Greenland or West Antarctic ice sheets. We don't know how quickly elapsed ice shelves would lead to accelerated glacier flow, or how long it would take for that acceleration to propagate inland. We don't fully understand all the feedback mechanisms at play, and we continue to discover nuance. Some of these gaps in knowledge may be filled by future research. Others may represent inherent unpredictability in a complex, nonlinear system. What we do know is enough to recognize that the changes underway are significant and that the risks are substantial. Every fraction of a degree of warming, every additional year of high emissions, every delay in transitioning to cleaner energy systems increases the likelihood of triggering large-scale, irreversible changes. The ice sheets are massive, but they're not invulnerable. The climate system has momentum, and changes set in motion now will continue to unfold for centuries. The story of Earth's ice is ultimately a story about change, resilience, and vulnerability. Ice sheets have grown and melted away repeatedly over Earth's history, reshaping continents and seas. Life has adapted to these changes, though not without extinctions and disruptions. The planet has endured asteroid impacts, supervolcano eruptions, ice ages, and hothouse periods. It has survived and evolved. But the question facing us now is not whether the planet will survive at will, but what world will inhabit in the coming centuries and what legacy will leave for future generations. The frozen archives of Greenland and Antarctica contain within them both warnings and wisdom. They tell us that climate can change dramatically and that ice sheets can respond rapidly once thresholds are crossed. They show us that sea levels have been much higher in the past and could be again. They remind us that the apparently stable world we've known is actually an unusual and precious interval of climatic calm in a planet prone to dramatic swings. And they challenge us to understand these systems well enough to anticipate their future behavior and to make informed decisions about how to respond. As research continues and our understanding deepens, the ice will keep melting or growing in response to changing conditions. Satellites will continue their silent vigil, documenting changes from orbit. Scientists will analyze their data, refine their models, and publish their findings. Policymakers will weigh options and make decisions with profound long-term consequences, and the rest of humanity will live with the results of these decisions. Adapting as necessary to a changing world. Asterisk the Earth's frozen realms. Those vast expanses of ice that have shaped our planet's climate for millions of years now stand at a crossroads. They're responding to the warmest conditions they've experienced in millennia, possibly in hundreds of thousands of years. The changes are real, measurable, and accelerating in many regions. Whether these changes represent the beginning of a catastrophic transformation or a manageable transition depends on actions taken in the coming years and decades. The ice itself cannot speak, but it records everything every warm summer, every storm, every subtle shift in ocean currents. Scientists read this record, interpret its meaning, and share their findings with the world. Asterisk the question is whether we'll heed the warnings. Written in ice before the thresholds are crossed and the changes become irreversible, the answer will determine the world our children and grandchildren inherit. Whether it's one where coastal cities still stand, where ice caps still gleam white at the poles, where the climate remains within bounds that civilization can manage, or whether it's a profoundly altered world with coastlines redrawn, climates shifted, and ecosystems transformed. The ice has survived millions of years of Earth's changes, but it has also vanished when conditions warrant it. We're determining now which path we'll take. Asterisks in the vast sweep of geological time. The present moment is but an instant, a brief flicker in Earth's 4.5 billion-year history. Yet it's an instant of extraordinary significance, a pivot point where the trajectory of climate for centuries to come is being determined. The frozen archives of the past illuminate the choices before us. They show us what's possible, what's probable, and what's at stake. They remind us that we live on a dynamic, ever-changing planet where stability is temporary and change is the norm. And they challenge us to act with wisdom, foresight, and care for the world we'll leave behind when our own moment passes and becomes itself a layer in the great record of Earth's history.